This unit was all about circles. In our first subsection, the objective was that students will be able to create an equation and graph of a circle given 2 points, and that students will be able to generate an equation of a circle given a graph. Our essential questions all stem from our equation of a circle. So the first is, what is the general form? The second is, what does each part of that formula mean? And 3, how are the distance and midpoint formulas used to create that said equation? A circle is a set of all points x, y in a plane that are equidistant from a fixed point. That fixed point is called hk, which we call the center. The distance r between the center and any point on the circle is called our radius. So this is the standard form, where hk is our center and the square root of r squared is our radius. So in the bottom left, we have a center at 0, 0 and a radius of 7. So in the middle, our center is 14, 2, and our radius is 2. And on the right-hand side, our center is at -2, 3, and our radius is at the square root of 183, which is approximately 13.5. So if you were given 2 points, you're able to write the equation of a circle. However, it depends on what 2 points you're given as to how you would approach writing that equation. So in situation 1, if you're given the center and another point, we already know our h and k, which means we just have to find our r, so we need to use the distance formula to solve for r. So we're given a point 1, 4 and a center at 2, 3. So we already know the beginning part of our equation, and we just need to find the distance, okay? And it doesn't matter whether I find the distance from the point to the center or from the center to the point. So I'm going to take the square root of x2 minus x1 squared plus y2 minus y1 squared. All right, so in this case, I went from the center out to the point. I'm going to get a radius of the square root of 2, which means that my equation is going to look like x minus 2 squared plus y minus 3 squared equals 2, because the square root of 2 squared is 2. In the bottom, it says that our center is at the origin, which means I have a center hk at 0, 0. I'm then going to find the distance from the center to the point on the outside, and I'm going to get my radius to be 5. So plugging that into my equation, I'm going to get x minus 0 squared plus y minus 0 squared equals 25. And simplifying that down, I can write it as just x squared plus y squared. I don't need the zeros. However, if you're given the end points of the diameter, you don't have the center. So you need to find the center and you need to find the radius. But what we do know about the diameter is that it cuts through the center of the circle. More specifically, it cuts through at exactly the midpoint. So we're going to use the midpoint formula first to find the center, and then we're going to use the distance formula once we have the center to find our radius. So in this first example, we found our center using the midpoint formula, and then I'm going to find the distance from the center out to either of the points, 6, 1 or 4, 5. What you'll notice is that no matter which point I use, whether I go from the center to the outside to 6, 1 or from the center to the other, I still get the same distance, so it doesn't matter. So our ultimate equation is going to be x minus 5 squared plus y minus 3 squared equals 5. Now, when given a problem like this, I don't need you to actually solve for both distances. Just pick one. So in our middle example, or our bottom example, we're again going to use our midpoint formula to find the center. We're then going to find the distance from the center to either of the points. We notice again they're the same, and our ultimate equation looks like x minus 3 squared plus y plus 2 squared equals 5. In the second part of this unit, we are able to write an equation of a circle by completing the square. Our essential question is, how do we know which strategy to utilize in order to write the equation of a circle? So completing the square is a technique used to convert a quadratic trinomial, that is a 3-termed polynomial with a degree of 2, that's not a perfect square, into a perfect square plus some constant. And we're going to walk through each of the steps below. So first things first, we took x squared minus 6x plus y squared plus 6, and we moved that 6, we moved the constant to the other side. And then we grouped stuff that looked the same, terms with x's and terms with y's together. Now here's the complicated part. We have to find that missing c value. And the way we find that is by taking the b value divided by 2 and squaring it. So I'm going to take -6 over 2, get -3, and square it to get 9. And I'm going to add that 9 on both sides. Can't just do it on the left or just doing it on the right. I'm going to factor both sides to get into the standard. I'm going to factor the left-hand side, and I'm going to add the right-hand side so that I can get the equation of a circle so that I can identify my center and my radius. So let's work through this example together. First, I'm going to move that constant to the other side, and then I'm going to group my x's and group my y's together. Now I need to find my missing c values. So for the first one, I'm going to take -8 divided by 2, that's -4, and I'm going to square it and get 16. And then I'm going to divide -6, cut in half is -3, I'm going to square that and get 9. I'm going to add both of those on the left and on the right, and I'm going to factor the left-hand side into something that looks like this so that I can identify my center and my radius. Let's try another one. This one, I need to move that -26x over to the rest of them, but I do need to move that 364 over so that it's on its own. I'm then going to group my terms together, solve for my missing c values, add them on both sides, factor, and then combine it all into an equation of a circle where I can identify my center and my radius. Let's do it again. First, I'm going to move that constant over. Then I'm going to group my terms. I'm going to find my missing c values. And then I'm going to factor to identify my center and my radius. In this third part of the unit, students will be able to understand the relationship between chords and angles and the arcs that they create. The essential question is just the ability to describe the relationship between central and inscribed angles. So a central angle is one that has its vertex at the center of the circle. Its measurement is equal to the measurement of its included arc. An inscribed angle is an angle that has its vertex on the circumference of the circle. Its measurement is half of the included arc. Therefore, the included arc is twice the inscribed angle. This is called the intercepted arc. So in the case of this ABC where we get angle D to be 86, we know that the arc on the outside is 86 as well because that's a central angle. However, because that outside arc is 86, we know that x, which is an inscribed angle, is going to be half of that, so it's going to be 43. On the left-hand side with our central angle, we know that our inscribed angle is 75, therefore our far arc, A to C, has to be double that, so it has to be 150, and if that's 150, then so is that x value. So let's work through a couple of these examples. In this first one, since our central angle is 139, our arc from G to I is also 139. We have an inscribed angle here on the left, so if our arc is 124, then our angle must be half that, and it must be 62. In this one, we know our arc is 167, and we have a central angle, so our x value is also 167. And in this one, we know that our inscribed angle is 96, which means that our angle x must be double that, which comes out to be, I think, 192, if my addition is accurate. In this last section, students are able to identify and explore properties of tangents and secant lines, and they're able to differentiate between them. Our essential question is, how do you determine the measure of angles and line segments formed by secants and tangents? So, a tangent line is a line that intersects a circle at exactly one point. They are perpendicular to the radius at that point. They form a 90-degree angle. So because they form a 90-degree angle, we can create a triangle and thus use the Pythagorean theorem to verify tangents. So let's work through this example together. We're asked to verify if BC is tangent to the circle A. So we've got the Pythagorean theorem as a squared plus b squared equals c squared, which really becomes the line segment AB squared plus the line segment BC squared being equal to AC squared. So we need to show that that mathematical statement is true, which it is. Therefore, we can conclude that that angle ABC is indeed a right angle. So slope of a tangent line, they are the negative reciprocal of the line at which they intersect. So if one has a slope of 4/3, the other one would have a slope of negative 3/4. So in this case, we have a slope of the radius being negative 2/3. So ours would be flipped and positive. So it's going to be positive 3/2. Here we go in our properties of circles, and if I am not mistaken, there are 5. So the first one is tangent, tangent. They are two lines that intersect outside of the circle, and because they look similar, this one's pretty easy to remember. We can say that they are congruent to one another. So AD is equal to AB, which means that x squared plus 2 is equal to 11, which means x squared is 9, and therefore x is plus or minus 3. In our second property, chord, chord, we have this mathematical equation that A times B equals C times D, where both AB are on the same line and CD are on the same line. So in our example, we would have 9 times x equals 3 times 6. So 9x equals 18, therefore x equals 2. In our third example, we have two secants intersecting outside. Notice the difference between a secant and a tangent. A secant cuts through, and a tangent just touches. So again, we have this equation, A times B equals C times D, but our A and B are a little bit different. A and C are both the measurements on the outside, and B and D are the length of the entire secant. So in this case, we would have LM times the entire length LN is equal to LO times the entire length LP. So we know that the outside LM is 9 and the entire length is 20. But on the other side, we know that the outside is 10 and we don't know the entire length. The entire length is not x. It is 10 plus x. So now I can distribute and subtract and divide to get that my x value is actually 8. Tangent secant, this is an interesting mix. So it's clear that we have a tangent line and a secant line. So it kind of combines the two. And we've got this equation that we would take our outside times our entire length of the secant is equal to our tangent line squared. So we've got that CB squared equals CD times CA. So 24 squared equals 12 times 12 plus x, because again, we don't know the entire length from C to A. We can multiply it out and solve for x. Lastly, we need to talk about angles that are formed by either secants or tangents. This is our equation, that far angle, in these examples it's angle x, we need to find the far arc minus the near arc and then divide by 2. So in this first example on the bottom left, AC would be considered our far arc, CH is our near arc, and our angle x is the one that we're looking from. So it's our point. So our equation is going to look like the far arc minus 105 over 2 equals 55. So to solve for that far arc, we would need to multiply both sides by 2 and then add 105 so that our far arc has an angle measure of 215. In the middle, we know our far arc, but we don't know our near arc. So we're going to do the same process to solve for our near arc. And lastly, in the far right example, we know our far arc is 178. We know our near arc is 102, but we don't know the point, the angle at which we're looking from. So we can plug it in and solve so that our angle is 38 degrees.